Welcome to this explainer. Today, we are demystifying the famously complex, highly rigorous UK ENA ERE G55 standard for connecting new assets to the grid. Now, if you're an electrical engineer or working in power systems, you already know this isn't just some minor regulatory update, right? No, this is a fundamental transformation in how we manage power quality in a rapidly changing electrical landscape.
So, let's take a quick look at our roadmap for today. We'll be hitting 1. The G5/5 harmonic standard. 2. Sharing the harmonic headroom. 3. The three-stage assessment. 4. Conquering stage 3. And finally, 5. Mitigation and compliance solutions.
All right, let's dive right into Section 1, the G5/5 harmonic standard, or as we like to call it, the noisy grid.
So, why is grid connection suddenly so much harder? Seriously, if you're a project developer or consultant, you've definitely felt the pain of these recent regulations. You've probably found yourself wondering, what exactly caused this massive shift? Why are projects that would have been totally rubber-stamped just 5 years ago suddenly requiring these massive analytical reports and super expensive mitigation hardware?
Well, the real kicker here is that our amazing new green technologies, they are incredibly noisy. See, traditional synchronous generators used to provide a nice, smooth sine wave. But modern inverter-based resources, we're talking solar PV plants, battery energy storage systems, EV chargers, they inject nonlinear currents directly into the network. This creates absolutely unprecedented harmonic distortion, especially at higher frequencies. Now combine that with the widespread use of underground cabling, which bumps up network capacitance and the risk of resonance, and you've basically got a recipe for equipment overheating, protection maloperation, and asset degradation. The old standards just literally couldn't handle the high-frequency emissions being pumped into our grid.
Moving right along to Section 2, sharing the harmonic headroom, which introduces a totally new paradigm.
We are fundamentally shifting away from a chaotic winner-takes-all system to a shared pie approach. Think back to the old G5/4 standard. Limits were absolute, and the first developer to connect could just eat up all the available harmonic capacity in a first-come, first-served free-for-all, until the grid was totally maxed out. Well, G55 completely replaces that inequitable setup with harmonic headroom apportionment. It treats grid capacity as a highly finite shared resource that actually has to be managed for both current users and future ones.
And that brings us to a huge principle of this new standard. Apportionment basically means the network operator looks at the total available headroom, the gap between the background noise and the maximum planning limit, and they divide it up. So a developer connecting at 132 kV or below is generally only allowed 50% of the individual harmonic planning limit for their incremental emissions. This is brilliant because it prevents the first project in the queue from hogging the entire limit with noisy equipment. It ensures vital capacity is left over for the next projects down the line. It's way fairer for sure, but it also means your individual allowance is significantly tighter.
Okay, Section 3, the three-stage assessment. Think of this as your hero's quest.
To prove compliance, G5/5 uses a tiered approach. Step 1 is Stage 1 for your simpler, low-voltage connections. Step 2 is Stage 2, which handles high voltage under 33 kilovolts. And Step 3 is Stage 3, the ultimate test, mandatory for anything at 33 kilovolts and above, or if you happen to fail any of your previous stages.
Looking a bit closer, Stage 1 is completely designed for low voltage, and it's split up into substages 1A through 1D. What's actually pretty cool here is that smaller connections can be fast-tracked. Like substage 1A allows complete self-certification for very small devices, under 16 amps per phase. But as you move down the line to 1C and 1D, that's when you'll start needing equipment power data, short-circuit power at the point of common coupling, and eventually, actual real-world background harmonic measurements.
Now for high voltage, you're entering Stage 2 territory, specifically substages 2A, 2B, and 2C. Here, your data requirements and network modeling needs increase dramatically. To pass 2C, you have to predict the total harmonic voltage distortion post-connection at the point of common coupling, and then compare that against the planning levels. This is a critical threshold, guys. If you fail 2C, there is no quick fix. You are forced straight into the heavy, complex modeling of Stage 3.
Which brings us to Section 4, conquering Stage 3, the final boss.
Under the old rules, you might have just used a simple fault level to base your calculations on. Yeah, not anymore. Now, the network operator hands you what are called harmonic impedance loci. These are basically sets of polygons mapped on a resistance versus reactance plane.
Because the grid isn't static, right? These loci have to account for everything: summer demand peaks, winter lows, and unexpected N1 outage scenarios. They represent the absolute worst-case harmonic impedance of the network for every single order.
And here is where it gets seriously intense. G55 pushes the assessment boundary all the way up to the 100th harmonic. The old standard only went to the 50th. So compliance literally requires proving your plant can handle the absolute worst-case point on every single locus they provide you. Meaning, you have to run thousands of individual Python automated simulations in your power system software to definitively prove your plant won't amplify resonances into dangerous instability.
But if you dig into the standard, there is actually a fascinating practical workaround. Because limits are based on that apportionment we talked about, sometimes the calculations hand you a limit so incredibly low that it's essentially just background measurement noise. According to the text, if your voltage emission limits at some harmonic orders drop below 0.1%, they can actually be capped at exactly that 0.1% threshold, unless, of course, there's a specific remote control frequency risk. This 0.1% floor is a game changer. It can absolutely save a project from completely impossible compliance targets.
Finally, Section 5, Mitigation and Compliance Solutions. These are your magic weapons.
Even if Stage 3 looks daunting, you can successfully conquer the standard by deploying a few key strategies. First, the hardware route, installing active harmonic filters. These actively monitor the line and inject inverse currents to perfectly cancel out the noise. Second, you can go back to the manufacturers and ask for highly accurate Norton equivalent models for your inverters so you aren't failing just because you used overly conservative generic data. Third, you might simply restrict your operational envelope during specific, rare grid contingencies rather than shelling out for massive filters. And lastly, you can negotiate conditional acceptance with a network operator, committing to rigorous post-connection monitoring to prove your real-world emissions are safe.
So, as you prepare your next grid connection, you've got to ask yourself, do you have the precise background data, the advanced modeling tools, and the mitigation strategies ready to actually navigate this rigorous harmonic landscape? G55 is a massive hurdle, no doubt about it. But by understanding apportionment, mastering those impedance loci, and really knowing your mitigation options, you can absolutely get your project connected safely and successfully. Thanks for joining me on this explainer, and I'll catch you on the next deep dive.